तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, last class we were discussing the variation of I squared L, that is the heterojunction I squared L, where the heterojunction bipolar transistor is used, and we have also seen the advantages of heterojunction bipolar transistors compared to the homojunction transistors. And in a heterojunction bipolar transistors we have seen that you even with a lightly doped emitter, okay, you actually get a large beta. Okay, and this largely offsets the problems of heterojunction problems of I squared L, because in I squared L the problem came about because you had to use a lightly doped emitter. Okay, and so there has been a lot of work on heterojunction I squared L, and even now a lot of work is going on. So we shall continue our discussion on heterojunction I squared L, and we have what we have been discussing in the last class. Okay, heterojunction I squared L or H I squared L. Okay, and we had seen that the circuit is like this, which is more which is rather similar to the Schottky transistor logic, except for the fact that this is not a Schottky transistor. Okay, so you have a resistance from power supply, okay, which acts as the current source, and this current can either flow into the base of the transistor, okay, in which case the transistor has to go to saturation and the output voltage goes low, or if the input is low, or then this current flows into the input, okay, and this transistor is cut off, all right, and you and the output is going to be high, in which case, all right. Now, and we had also derived a particular relationship for the relationship or a condition for saturation of the transistor, and we had seen that for in order to ensure that the transistor goes to saturation, beta must be of the transistor must be greater than VCC minus VSD plus VCE divided by VCC minus VBE, correct? All right. Okay. So this was the relation which we had into, of course, the fan out, that is the number of outputs of that particular transistor. Okay. So this was the relation which we had derived in last class, and if you can just plug in some values. Okay, suppose VCC is equal to 3 volts, okay, and you see that the values, the Schottky diode cut-in voltage, see these values are going to be a bit different from what we normally encounter, because of the fact that this is a Schottky diode on a compound semiconductor material, that is a material with a larger band gap. Okay, so the cut-in voltages are going to be much higher. Okay, so the Schottky diode the drop is 0.7 volts, the base emitter voltage is 1.3 volts. Okay, and of course VCE, that remains as that is also that is normally, VCE is around say 0.3 volts or so. Okay, that is when it goes to saturation. So if you put these values, and for a fan out of 4, say you have 4 collectors, 4 fan out, so beta will be greater than 3 minus VSD plus VCE is 1 and VCC minus VB is 3 minus 1.7 sorry 1.3, okay, and this works out into 4, this works out to be almost equal to 4.5. So, you see that a small beta is required in fact to ensure that the transistor actually goes to saturation, okay. All right. So, the circuit, there is no problem as such for the circuit to function properly, okay. All right. Now, what is the structure? I just will give you the structure, that is the cross sectional view of this device, okay. How does it look like? Well, in fact, you see that most of the compound semiconductor devices are fabricated using epitaxial wafers, where most of the layers used in the fabrication of the devices are grown epitaxially. So, the processing is as such after that becomes quite simple. So, what you have is as a starting material is a 3-layer structure. You have N plus gallium arsenide, N plus aluminum gallium arsenide. We have already seen last class that aluminum gallium arsenide is a wider band gap material. So, basically this acts as the emitter of the transistor. This N plus gallium arsenide is used as a contact material, because it is very difficult to take contact from aluminum gallium arsenide. Being a wide band gap material, it is very difficult to get an ohmic contact. So, basically this is the emitter, okay. This N plus L gas acts as the emitter, and then what you have is N type gallium arsenide, okay. All right. So, this is the starting material what you have. What is done is then some implantations are carried out, okay. That is, you implant some material. So, what you do is there are 3 implants basically in the whole device structure, okay. 3 implantations, one for the P plus base, okay. So, what is done is this region is converted to P plus base, all right, and then you have for P plus base contacts, you have, so these are the base contact regions. See, the implantation, I think as some of you may be aware that through implantation it is possible to form a junction beneath the surface, okay. That is the difference between diffusion and implantation, okay. For diffusion the entire region has to be P. So, here what you are doing is depending on the energy of the implant, okay, the element which you are implanting can be implanted deep inside the semiconductor. So, this P plus implant which is done, okay, it is done under the surface of the semiconductor, so that this region of the semiconductor becomes P plus, all right, and then you do a normal implant like this, all right. So, this is P plus. So, basically this is to take contact for the base, all right, and then there is another implant for isolation, okay. Usually in this gallium arsenide material, boron is implanted at high energy and it creates a lot of damages in the semiconductor, and it basically creates a very high resistance region, okay, which acts as an isolation, okay. So, this is isolation region, okay. So, the basic device structure is you see an NPN transistor, okay. So, NPN transistor, the P contact is taken from here, that is all, okay. Then what remains is you have to take the collector contacts from here, okay. So, this is the base contact, this is the base contact, this is the collector, and these are the Schottky diodes, all right. then what is the remaining is you have to make a resistance. Okay. So, what is done is a thin film resistance, okay, material is deposited here, all right, and on the isolation region, okay, and this acts as a thin film resistance, okay, and this is VCC. So, this is the resistor material. If I take a colored chalk, so this is the resistance material, okay, some material which is deposited on there which gives a certain resistance, okay, a thin film is deposited, okay, and you make contact to the P region which is the base, all right. So, what you have if you look at the structure, okay, so this is VCC. So, VCC, I will redraw the structure from here. So, VCC through a resistance it comes to the base of the transistor, all right. So, VCC through a resistance comes to the base, you have a transistor, all right, this is the base, you have NPN transistor, emitter is grounded, all right, and from the collector, this is the collector region, from the collector region you have various you have number of Schottky diodes, all right. So, it is coming out, all right. So, this is the particular structure, and this is the structure of the heterojunction I squared L basically. So, this is you see once you have the wafer, it just a few implantations, okay, and you get this particular device. Okay. So, this is the heterojunction I squared L structure, which is a rather simple structure as such. Okay. And of course, the important thing is because of the larger wider band gap material as emitter, okay, you know that the charge storage is going to be very small, okay, and that is the most important thing here. Okay. So, this type of structure was proposed and a lot of work has been done at Texas Instruments, okay, and I will just give you the reference again if you want to for further reading, okay, H.T. Yuan and others. IEEE transactions, electron devices, volume 36, pages 2083 to 2092, 1989. Okay, it's all right. So, where this heterojunction I squared L was proposed, in fact, they have been working on this particular they had been working on this particular structure for a long time, and in fact, they have also fabricated a microprocessor. Okay, in this paper they had reported that they had fabricated a 12,872 gate mu-p using H I squared L and with a clock frequency of 125 megahertz. Okay. Now, well, 125 megahertz may not sound very high, but you must remember that this was in 1989, okay, when you did not even have the 486, okay, I think, all right. So, and at that time, 125 megahertz was a very high clock frequency for a CPU, okay. I think it was those times 386 and all used to operate below 50 megahertz, okay. So, this was a high frequency, and also for the gates for a 1.5 micron process, and a fan out of 4, the delay for the H I squared L was obtained as 150 picoseconds, okay, at at power dissipation of 5 milliwatts per gate. Power dissipation was a little higher side, but the delay was at, for a fan out of 4, okay, the delay was just 150 picoseconds, and a fan out of 1, the delay was just 85 picoseconds. All right. So, a fan out of 1, the delay was 85 picoseconds, and for fan out of 4, the delay was 150 picoseconds. So, you see that this is a very high speed I squared L, all right. Okay. Go to sub 100 picoseconds. The point is, after 1989, okay, not much report has come out of this, okay. Although at that time, okay, this was really a very high speed device. One reason is, of course, you know that the compound semiconductor devices are rather expensive, okay, and that is why it is very difficult to market them, okay, compared to others. And also many of these companies, okay, you can do it for research purpose, but once if you go for production, it requires a lot of investment, okay, and many of these companies are not willing to do that maybe. That could be one reason, I think, but really we have not heard much about it later, okay, although it was very promising at that stage, okay. All right, but okay. Then, but a lot of work has been going on also from other people also in this area about heterojunction I squared L. In fact, there has been a very recent report, I should say it is as late as December 1998. I will again give you the reference, okay, just if you want, just to give you an idea of the research which is going on in this area, okay. Wainwright and others, IEEE transaction electron devices, volume 45, number 12. December 1998, okay, that is the latest paper I have seen on this topic, okay. And what they have done in this paper, I will just briefly tell you that they have examined, okay, different structures. This is mostly simulation work what they have done. They have examined many structures of heterojunction I squared L, and they have studied especially one particular structure which was proposed initially, what is called substrate fed logic. Substrate fed logic, SFL. This is another variation of I squared L basically, where the injector, you know, is at the bottom, okay. So, I will just see show what the structure is that they have studied, okay. So, you have the injector is at the bottom, okay. That is the idea of substrate fed logic, okay. That is, the injector contact is from the bottom, all right. So, you have a P, you have an N, all right. So, PNP transistor is actually a vertical transistor in substrate fed logic rather than a lateral transistor. So, you have, this is an isolation, this is N contact from here, all right, and you have a layer of silicon germanium here. So, this is a silicon, all right, this is a silicon device, this is silicon germanium. Now, silicon germanium is also a heterojunction, okay. Silicon germanium has a lower band gap compared to silicon, okay. And so this is a heterojunction, all right. And then you have, so this is a structure which one of the structures they have studied, okay. So this is P plus and this is N. So if you look at this structure, what you have is a PN, this is P type silicon germanium, okay. Now this silicon germanium, this is the only region which is silicon germanium, and the remaining part is silicon. So basically the silicon germanium has been grown epitaxially, okay, and this has been done selectively. Nowadays it is possible to do growth selectively. Okay, in certain regions you want to do silicon germanium, that is also possible. So basically you have a silicon germanium here and the other regions are all silicon. So you have a PNP structure, all right, a PNP, this is the injector, okay. And so this P region is actually the V in point, all right, input point, and you have the NPN, all right, NPN, okay, transistor. So for this transistor, okay, this is the output, this is the collector, okay, this is the emitter of the NPN transistor. So this is grounded. See, this is basically contact for this point. Okay, this side you have taken the contact for this point. So this is the NPN transistor, all right. So I can put it this way, this is the collector of the NPN, okay, this is the base NPN transistor, all right, and you have a PNP here. So this is also P type, okay. Okay, and this is the PNP of the, I'm sorry, this is the emitter of the PNP, okay. So what do you have? This is the injector terminal. So you have a PNP and you have an NPN. All right. The PNP emitter, this is the injector point. The N of the PNP, that is the base of the PNP, is the same as the emitter of the NPN. Okay. So this is the same as the emitter of the NPN, and this point is actually grounded here. All right. This N region is actually grounded. Okay. So this is the ground. All right. The collector of the PNP is the same as the base of the NPN, and this is the input point V in. All right, and you can have multiple collectors like this. Okay, just one collector is shown. Of course, you can have multiple collectors. All right. Now, so this is a basic I²L structure. Okay, and what they have done in that paper is actually they have analyzed the structure, they have optimized this structure, that is they have taken different dimensions, different charge storage in the different regions, okay, and they have done a thorough analysis, okay, and also made small modifications, slight modifications of the structure. I do not want to go into it because it becomes more complicated, but the interesting thing is that they predict that with this particular structure one can actually go down to a switching speed of 34 picoseconds at a minimum geometry of 1.4 micron. All right. So that is the outcome of their work. So basically what I by going through this, what I want to impress is, number one, there is still a lot of interest in I²L, you know, in terms of as a logic family, although it had a problem of high speed, and people are working at it on it, okay, and to reduce the delays, okay, and see how it can be improved, because if I squared L has its inherent advantages, that is, it's got low power dissipation and high packing density. If you can couple speed with that, it is going to be a very powerful logic family. So people are working on that, and there are one way to do it is heterojunction I squared L, and in fact the delays one talking of is quite remarkable. Okay, it is just 34 picoseconds, which would really make it a very high speed logic family. Okay, although we don't really associate I squared L, we don't really call I squared L a high speed logic family. Okay, so that is the why I wanted to introduce this to you, and this is a very recent work. Okay, all right. So with that, I think we come to the end of this discussion on high speed. I mean the different efforts which is going on in order to make I squared L a high speed family. That is, from technology wise, okay, that we have seen how self aligned technology improves the speed, okay, reduces the delays, and then these efforts, that is some circuit modifications like the Schottky transistor logic, as well as this heterojunction I squared L concepts. Okay. So before we actually close this topic on I squared L, I'll just one or two small points I would like to make about I squared L before we move on to other logic families. Okay. See, I squared L, one of the major advantages, as we said, was power dissipation, was low power dissipation, because, and one of the reasons behind that is that you require a very low power supply voltage. Okay, the maximum voltage in the circuit, okay, is going to be around 0.7 to 0.8 volts. Okay, that is the base voltage. Okay, it does not exceed beyond that, because if you look at this circuit here, this particular I squared L cell, okay, this is ground, so this voltage cannot be, this is for this to be, sorry, for this voltage, this junction to be forward biased, this, okay, this junction, this voltage at this point cannot exceed say 0.7 to 0.8 volts, because you cannot forward bias a junction beyond that. Okay, I am talking of silicon again, all right, and of any junction, okay, if this voltage also cannot be more than that. Okay. So you see that that is the limit. So in fact, an I squared L circuit can be operated at a power supply voltage of as low as say 1 volt or something. Okay. So what you have is, so this is the emitter of the PNP, okay, and if you have other circuits, okay, you have, this is a common point, okay, all the emitters of the PNPs are common, and from there you can have or you can even consider this as a multi collector transistor, okay, and this goes as current source to different nodes. Okay. Now, so basically you can consider the I squared L as, this is a power supply, you have a resistance, and this is the I squared L circuit, I squared L block. Okay. And this voltage here is going to be around 0.7, maybe slightly more. Okay. And this voltage, so you can control the current which is flowing in by using this VCC and R. Okay. And you know, we have already seen that the effect of current on the various parameters like noise margin or delays, etc. Okay. So it is an important thing. Yeah. But now you see, one interesting thing is that in many circuits, okay, many systems, all right, you may have a system where not all the circuit is made out of I squared L. Okay, you may have part I squared L, the other parts may be TTL or any other, some other logic family, and you may want to have a common power supply voltage. Okay, that is, you have a common power supply which is driving the different parts of the circuit. Okay. Now, so what this VCC may be 5 volts. Okay, if you are having other, this VCC goes to TTL part for example, you require 5 volts, okay, and so this is say 0.7 volts, okay, and the same current is flowing through this resistance and this I squared L. So, what are you having? See, you have a low power circuit here, but if this is 0.7 and this is 4.3, 6 times more power is dropped in the resistance compared to the I squared L. So, actually having a low power circuit is no use, because you are just wasting the power in the resistance, is not it? I mean it is more than, so the current flow, all right. So, you have a large power drop, basically you have a large power drop in the resistance, okay. So, can you do? So, can we have change the I squared L circuit in some way, so that you have a higher, you have the same power dissipation, but you have a higher voltage here, but say less current, okay. You understand, that is, suppose instead of 0.7 volts I can have 1.4 volts here, okay, at drawing half the current, okay. I would save on power, okay, which is wasted in the resistance, okay. So, that is the idea which people working, and they came up with particular types of I squared L called stacked I squared L. Okay. So, basically what you have in a stacked I squared L is you have this is the current source, okay. So, you have circuits like this, okay, all right. So, this is the I squared L, this is the injector, all right. So, this is the base which goes to ground here, okay. So, this is the one I squared L cell, okay. Now, what you have is here again you have other circuits, sorry, okay, and for example you can have different levels, okay. That is, see what you have now. So, this is one level, okay. So, you have 3 levels of circuitry here, okay. So, this is the injector and this is going to the base, okay. I have just drawn it like this, you can have more complicated circuitry. So, what you have is the going to the base, all right. This is one level of I squared L circuitry, and from here this is going again to the injector, to another injector, okay. So, whatever current flows in this, so all the current must flow back again in this way, okay, all right. And again you have another level of I squared L circuitry, and again, so all the emitter currents must add up, all the currents flowing into this level must flow out of this level, okay, and this whatever flows out flows in as injector current here, all right. And again you have another level of circuitry, okay. So, what you have done is, so if you have a large circuitry say in one level, okay, and you can break up the circuitry into 3 parts where there is no interaction as such, okay, between the different parts, okay, and fabricate them at different levels, okay. So, what you have done is, you see that this voltage is 0.7 volts, this one will be 0.7 volts, this one will be 0.7 volts, okay. So, the entire circuitry would be 2.1 volts, okay, and since the amount of circuitry in each level has reduced by 1/3, okay. So, the current which you require at each level is reduced, okay, all right. So, you are consuming the same power, but what you have done is the total voltage drop across this circuitry has increased say 3-fold, and the current has reduced by 1/3, Okay. Now, if you again go back to this model which we have here, now if this is gone up to 2.1 volts instead of 0.7 volts, and the current which is drawing here is 1/3. Okay. So, the power dropped in this resistance is going to become 1/9 of what it was drawing initially. Okay. So, basically you have saved a lot of wastage of power. Okay. So, this is particularly useful when you are fabricating when you have circuits, different types of circuits, okay, which is driven by a common power supply. Okay. So, this is one type of stacking. Okay. There is another type of stacking which also I will just you have a current source like this, which is again as a PNP transistor. So, you may have something like this. Okay. These may be two inputs, just like in a normal I squared L. Okay. And then you have another transistor here, and you may have another transistor here. Okay. So, here what is the logic here? It is a NAND logic. Okay. Okay, because it is at the collector. So, this is the output at the collector of some transistor. Okay. So, this is the NAND logic, that is, if any of these inputs go low, okay, if A or B goes low, okay, what happens is this current is going to flow this way, the transistor is going to cut off, and the output is going to be high. So, NAND is, if any input is low, output is high, that is the logic in a NAND gate. Okay. So, this is AB bar. So, if you have C here, that is another input. Okay. What is the output here? This is going to be ABC bar, that is, if any of A, B or C is low, output is going to be high. See, if A or B is low, then what happens is the current is flowing this way. Okay. So, this transistor emitter, there is no current. Okay. So, there is no chance for this transistor to go to saturation. Okay. Only when A and B both are high, okay, then only this transistor turns on, okay, and then only this the second level transistor has a chance. Okay. This emitter current can flow in as base current. Okay. And so, if now C is low, this current, emitter current will flow into the input. Okay. This transistor is off, but if C is also high, okay, then only this transistor turns on and the output goes low. So, only when A, B and C is high, then only it is high. So, if you have D here, okay, you have A, B, C, D bar. This is the NAND of A, B, C and D. So, this is another concept, okay, of stacked I squared L. All right. Both have been can be used. It depends on, it also depends on what circuit you want to you are doing. Okay. In some cases it is advantageous to use this type of stacking, in the other in some cases it is advantageous to use the other type of stacking. Okay. So, these are some of the concepts of stacked I squared L. Just one further point on this stacked I squared L, that is it possible to have the output of one level going to the as input to the other? All right. It is possible. Okay. The only thing is that in some cases you may have to do a level shifting. Okay. In fact, I think it is you can see for yourself that if you take the output of one lower level transistor, okay, and you feed it as input at a higher level, say here, okay, the output of one lower level transistor and feed it as input at a higher level, okay, level shifting is not necessary, you can do it directly, okay, because of the fact that if this transistor is cut off, okay, if this transistor is really cut off, then this is not drawing any current. Basic idea is when this transistor is cut off, this should not draw a current, and this current source current will turn on this transistor. So, there is no problem if this transistor is cut off, this is not drawing a current. When this transistor goes to saturation, okay, current will flow in here, okay, and the upper level transistor here is not going to go to saturation, it is going to be cut off, okay, no problem. But the problem is that if you want to take an output of an upper level transistor and feed it as input to the lower level, that cannot be done. Why? Because you see that if you assume that the voltage levels are shifted by 0.7 volts, okay. Now here if this is the at the emitter of the second level, if this voltage is 0.7 volts, okay, and when this transistor goes to saturation, this collector emitter drop is 0.2 volts, is 0.9 volts, okay, and if you feed it as the base of this, okay, you expect this transistor to be cut off, but 0.9 volts is not going to cut off that transistor, all right. So level shifting is necessary, okay, if you are feeding the output of an upper level transistor to a lower level transistor, okay. I mean the collector of an upper level transistor is fed as input to a lower level, but if you are feeding the collector of a lower level transistor to as input to the upper level, it is not necessary. This is true for both the types of stacked I²L, okay. So one has to take care of that. That is, level shifting means you may have to drop the output of the voltage by one diode drop, okay, 0.7 volts, okay. So you may have to shift the voltage down. So it is possible to interact between two levels, okay, with the level shifting, okay. But when you design, I mean stacked I²L, you should see to it that the levels are so chosen, the circuitry at each level is so chosen that there is minimum interaction between levels, okay, because that will add to problems, okay. The problem is of course that here you see that one has to really isolate each level, all right, because this all these emitters are shorted in one particular level, okay, but this is not ground actually, all right. So this emitter point for this set of transistors is different from the emitter point of this set of transistors, okay. So you cannot have a common substrate in which you fabricate, all right, you have to isolate them, these each individual levels. So that creates problems also from technology point of view. Okay, so that is about stacked I²L, one point. The last point I would like to make is I²L by its you know that the voltage levels are different from the normal TTL levels. So if you want to interface TTL I²L with TTL, okay, TTL is generally assumed as a standard sort of, okay. So you have to have, there must be some intermediate circuitry, all right, how to do it. So suppose you have an LSTTL, I just drawing the two ends of the circuitry. So this is the input side of an LSTTL, and the output side you have, well, you have a something like this. These are of course Schottky diodes, okay. I am just drawing, I am not drawing the internal circuitry, just the two other ends. So what you do is, suppose you want to LSTTL, so suppose you want to interface I²L with LSTTL, what do you do? Okay. Now I²L NPN transistor, that is all right, this output has to be fed as input to the TTL, okay, very simple. This output transistor, you put a resistance, same 5 volts maybe, okay, and this can be fed directly to TTL, okay. That is, if this transistor goes to saturation, okay, this 0.2 volts at the collector, okay, so this is going to be seen as a logic low by the TTL, okay, and if this transistor is cut off, all right, I mean this it is going to be seen as a logic high, okay, all right, this voltage here is going to be seen as a logic high by the TTL circuit, okay. So it is very simple, you just connect resistance here, okay, all right, and you can connect it as input to the TTL. On the other side, if you want to connect if you want to give the LSTTL output as input to I squared L, what do you do? So basically what you do is you make a sort of potential divider type of circuit, and this can be fed as input to the I squared L, all right. Okay. Now, basically idea is that this input here, if this input is low, okay, this transistor must be cut off, all right, and if this input is high, this transistor must go to saturation. Okay. Basically you also have a current source here, you must remember this input. Okay. Now, you see that if this is low, that means this when is this output low? When the lower transistor is in saturation. Okay. So, this voltage is goes to 0.2 volts. Okay. So, there is no way this transistor can turn on, because this voltage at the base is not going to be any higher. Okay. And when this transistor, when the output is of this TTL is high, that is this transistor is off and this transistor is on, okay, the current is going to flow into it, flow in here, and basically this is not going to sink any current, okay, all right. So, the whatever current source here, okay, this current is going to flow in here, okay, into this transistor, and it is going to turn on this transistor. Okay. So, this resistance values one has to actually choose proper values, okay, depending on the voltages that can be done. So, basically you have a circuit like this at the input, okay, and which can be used to interface the TTL with the I squared L. All right. So, I think this brings us to the end of this topic on I squared L. So, we have gone through this topic of I squared L. I squared L, well, it was, as I just briefly summarized, it was invented in 1971, early 1970s in the Philips laboratories as a circuit concept. It was very in those days it was a sort of revolution, and lot of work was done in that level, okay, because of it was felt that it is the as a bipolar logic family, okay, one can really go in for very large scale integration. Okay. The notable things was that there is no resistance in the circuit, okay, the low power dissipation, these are the two important things, okay, with respect to large scale integration. Okay. And but the problem was, of course, it had high delays, okay, because of the very structure, all right. And as we had seen that lot of work has gone on to improve in this aspect, and technology wise, technology has been improved, okay, and using self-aligned technology one can actually reduce the power dissipation, reduce the propagation delay, and also other circuit variations like Schottky transistor logic has been tried out, and also heterojunction I squared L, which actually is the area where people are working at present in this I squared L field, okay, and maybe, okay, in future, all right, heterojunction I squared L will really become very attractive because it has got all the advantages of high speed, okay, low power dissipation, and high packing density. Okay. So, the only thing is, of course, in this heterojunction I squared L, all these heterojunctions, the problem is nothing to do with the circuit. Actually, it is more expensive than silicon, okay, and so that is one of the reasons, okay, one of the things that has to be sorted out, okay, and once if it is done, if it happens in the future, maybe this will become very popular. Okay. With that we close this topic on I squared L, and next class we shall start on ECL.